Okay, and it's a great pleasure to have Sasha Zhiboedov here. He's going to tell us about Analytic toolkit for the S-matrix bootstrap, elastic unitarity, and extended analyticity. So Sasha, please.
Thanks, Zvi. Thanks for the invitation. It's a great pleasure. I will talk about the work which is trying to wrap up with Miguel Correa, who is a PhD student here, and Amit Sever. And also it's part of a bigger project which we're also doing with Madalena Lemos. So this would be an amplitude talk. It would be a bit technical. I hope I will try to explain the idea and give some technical details, but please interrupt and hopefully it will be clear what's happening. Now I cannot change the slide. Interesting.
Oh, you might have to.
Okay, now it works. Can you see it? Yeah.
Yeah.
Okay. So in this talk, I would be interested in scattering relativistic unitary gap theories in high dimensions. By high, I mean d larger than 3, and we'll be starting from general principles. Well, one famous fact about these situations is that we do not have known solvable examples of such theories, and it would be great to have one. Now, recently, there were a couple of success stories of which seem to be related. One is that we can take some strongly competent, importantly high-dimensional CFTs, like CFT3 in this. On the left plot, you see here this exclusion result from numerical bootstrap for the 3D Isaac model. And the idea is that by zooming in, you can, in some sense, at least in maybe very limited, but in some sense, solve the theory. And in the right-hand side, so this right plot, you see this plot from a recent paper by Pedro Vieira and collaborators, and he explained this talk in his talk last week at the Amplitudes conference. And here again, you run some sort of numerical bootstrap game, and you find some islands, and at the boundary of this island, you have some special point which are exact theories, which are, again, in a sense, even if you didn't know about them, you would have found them and you solved them. Now, the plot on the right corresponds to scattering in two-dimensional theory, and the big questions that we would like to understand, of course, I will not have an answer to this question in this talk, is that are there bootstrap solvable S matrices in D larger or equals than 3? So that's what we want to have. And you see, so the hope is that, okay, high-dimensional CFTs are solvable in this sense. 2D S matrices also seems to be of the same type. Maybe we are lucky, and we can solve also some interesting theory in high dimensions in some sense. Now, there is one interesting fact about these numerical methods is that they tend to produce, when you get something special in these plots, they tend to produce scattering amplitudes which are almost purely elastic. So they do not have particle production. And in this plot, for example, all these points on the boundary, they correspond to particles, to theories which are integrable. And okay, in two dimensionals, it's fine. There are interesting integrable theories, but in high dimensions, they're not really. And you want to have theories with particle production, say in, I don't know, something like UCD or gauge theories more generally. So we have to somehow improve these methods and to try to improve them in such a way that we get theories with particle production. This is something we would like to do, of course. Now, one way you can think of tackling this problem is that you explicitly include higher point amplitudes in your calculation scheme. So usually people do bootstrap like in CFTs or amplitudes for 2-to-2 scattering to 4-point correlator, but you can try to include higher point amplitudes. So, and this might be possible in 2 dimensions because the kinematics is much simpler, but it sounds hard in high dimensions. And in fact, you probably heard often people say the S-metric theory has failed. And when people say that, they usually mean maybe different things, but I listed three. So first is this general program in the 60s, they failed to understand the analytic properties of multi-point amplitude, which is something which exactly above I mentioned, something that might cure this issue with elasticity. They also failed to produce a controllable calculation scheme, which is obviously a problem. And then, of course, the S-metric theory failed to solve the pi-on-pi scattering. So that was sort of the golden standard, and QCD did much better. Now, with point 2 and 3, there is this new approach which requires some luck, which is that, okay, you don't try to solve pi-on-pi scattering explicitly, but maybe you try to explore bounds, and you look for special features, and maybe if you're lucky, you can solve the theory in this way. So in this sense, the number 2 and number 3, okay, it doesn't sound like a problem. People in the past, they had a different approach. They try to somehow directly guess pi-on-pi scattering. So let's not do that. But number 1 sounds like a problem. From what I told you, that indeed analytic properties of multi-point amplitudes, it's a very hard beast, especially if we try to think about them non-perturbatively. So I don't know if it's possible. It hasn't been done. But the point of my talk here, so one of the message is that you get into this problem in higher dimensions, namely in d larger than 2, because the kinematics gets more complicated. But also there is something else that happens in d larger than 2, which is nice, and maybe there is some hope, and there is this something else that happens, allows you to play this numerical bootstrap and together with some analytic schemes game where might not be necessary to get into this business of analytic properties of multi-point amplitudes to understand the particle production, at least partially. And what is this extra structure that you get? I will try to explain. So in the end, we have some proposal what you have to do and how you would like to modify the current approach, say to numerical bootstrap, to take care of this particle production. Maybe then we might hope to land on a physical theory. This is, at the moment, it's a far call still, but that's where we are aiming at. And so I hope it's clear. And this is the outline of my talk. It's a bit complicated, so essentially I will try to, so let me just zoom out first and to explain what I will be doing. So first I will be sitting in d larger or equals than 3. And the idea would be that we will use the basic principles of analyticity, crossing, and unitarity. I will explain a little bit more. We will use extended analyticity and elastic unitarity to essentially the upper part of the slide. We will start from low energy, low spin data, something that is measured in the experiments, scattering lengths of partial waves at low energies, and we try to fix the whole amplitude, of course with some error in terms of this data. So, and then after we have done that, we can try to implement into numerical codes, and as I will try to explain, this will also lead to this particle production. And so essentially I will try to explain what this scheme is, how you start from low energy and low spin data about the amplitude, and you try to make your way to understand how general principles constrain the form of the amplitude. And so I'll try to explain every symbol, every word and every error on this plot. But that's just to make sure that I'm not losing you. That's the aim. So I will slowly develop and make my way through the basic bounds. And so similar ideas, as you see, they were in some form and some variation pursued in the past. I will comment on it later. So let me make a historical remark. This is a sort of anecdotal story, but in one of the papers in this new version of S-metrics bootstrap, after great results, there is this note where the author says that after we found a surprisingly unknown 44-year-old paper, which beautifully in 2 pages does great things, which we rediscover. And then there is this footnote 17, and it seems like we are the first one to cite it. And this is quite remarkable about the subject, because we also we find constantly rediscovering many things and citing them for the first time. But I think that the whole approach and this philosophy is novel, and it's definitely worth revisiting and making these things clearly and trying to putting them in the perspective and a little bit with a different mindset.
Sasha, can I just ask a quick question before you continue?
Yeah.
So is there an obvious kind of one-line argument why forbidding particle productions in higher dimensions makes the S matrix trivial? The usual argument involves some symmetry, but is there an argument just with particle production?
I was planning to present the argument. It's very, very elegant. That it is known as a statement as Axe theorem in the literature. It's not theorem in the super vigorous standard, but it's pretty convincing, and it says that the scattering implies production in D higher than 3, but essentially in my talk I will try to explain the structure. I don't know how to say it in one line without explaining the structure, because the argument is
but it can be said without referring to something like a symmetry that
The argument will be based on these things: extended analyticity, crossing, and unitarity. So, and it's quite neat. So I hope maybe I'll tell the argument and you will tell me. Ask me again.
Okay, cool.
So and for example, one interesting fact about old literature, which you might not know, is that there are actually two A. Martins, which you might easily confuse because they appear on papers as A. Martin, but they're different people. One is a famous one who derived this Froissart-Martin bound, which he points to as a cross-section bound. And then second, Martin, whose papers also were very useful. We don't know. I don't know about his fate. I actually will be curious to learn what happened, or if he's still in physics. But anyhow. So that's my plan. I will start with the setup. I will try to lay out the assumptions. I will then try to explain the basic tools. It's a bit technical. And then I'll try to explain you the bootstrap scheme, which will in particular involve answering Thomas's question. How do you see that scattering implies production in high D? Some basics. So just when I say we have relativistic gap theory, what do we mean? It means in the far past and in the far future, the state of the system is described by a set of free particles. These free particles are on shell. The Hilbert space is just a Fock space of multi-particle states. S matrix. Now you have this Fock space of free particle states. You have a unitary operator which acts on it. If you want to be more rigorous, it's a kernel that acts in a space of square integrable wave functions, and then you can add some mathy words that it becomes a tempered distribution. So in general, it's not really a function; it's a tempered distribution, or it's a distribution which gives you some nice results when integrated with external wave functions. But these are technical details. Now, since the theory is gapped and is local, the S matrix admits clustering, which is a statement that if you separate wave packets, they do not interact much. And mathematical, it's a statement about factorization of this S matrix into connected and disconnected pieces. This is also familiar. Now, another simple non-perturbative result is that we're assuming that one particle states are stable, and Lorentz invariance completely fixes this one-to-one transitions. It's here. And since one particle is stable, it does not decay into more than one particle. So these elements are zero. And then, again, because the theory is relativistic, there's connected matrix elements that they have this conserving delta function. And then what multiplies is this T, which will be, of course, the main character. So this is very general. It's true. It's probably even true in gravitational theories, even though it's harder to prove. Anyhow, this is general facts. Now, I will be talking about 2-to-2 scattering. Now, in 2-to-2 scattering, what I told you is that then the 2-2-2 S matrix element involves a disconnected piece. There is one missing here. No, it's fine. Sorry. There is a disconnected piece, which is this one, and the connected piece. And the connected piece is again has this momentum conserving delta function and the function of Mandelstam invariants, which are standard things. And written here, basically you have an energy and an angle, and depending where you are on this Mandelstam plane of S, T, and U, you describe different processes. You know, if S is larger than 4m squared, T is negative, you in the channel 1, 2 goes to 3, 4. If T is larger than 4, it's negative, you go to 1, 3 to 2, 4, etc. So this is the standard stuff. So think of this would be the rest of the talk about this function of two variables. Now let me list the assumptions, and I will comment more what we assume about this function. First, we will assume what is known as extended analyticity. I will explain now, so you don't have to understand what it means, but I will assume certain analytic properties, and this analytic property, I marked it in red because it hasn't been proven. So people spend a lot of time proving things, and this is not proven, but this is sort of a natural assumption which seems to be consistent with general principles. It's hard to prove. It's also been used in the numerical algorithms, and it seems to be a natural assumption. But in principle, if you at this point you can say, okay, this is not rigorous because we assume extended analyticity, and nevertheless I will assume it because it allows me to play this interesting game. Now the second is the polynomial boundedness, which is a statement that the amplitude does not grow faster than polynomial. So in general, this has been proven in some subdomains of S and T. However, I will assume it for any S and T. I think it's also something very natural, but strictly speaking, all this old theorems were proved are less powerful than that. Then, as follows from general principles, and as I tried to mention briefly, this T S of T, in principle, it's not a function, it's a distribution because it appears as a boundary value of analytic functions. And so then you might, in principle, encounter that T of T, which stands for discontinuity of the amplitude, which is roughly, you should think of the cross-section. It's people try it, but it's very hard to prove from general principles that it's actually a smooth function. You can, in principle, imagine the cross-section has some singularity, and then, but I will assume that cross-sections are functions, and sometimes it's related. There's an interesting discussion to macro-causality, but in the past, finally, people argued for this using Goldberger's principle, which is that it is absurd that nature could be so unkind to us. Meaning that it's such an esoteric and crazy possibility which would not let us do things that we like. So let's assume that it doesn't happen. And then there are things in black, which are the assumptions which has been proven. And the first two is a crossing and what is known as a real analyticity. And the last one is a technical assumption, which just simplify my life. I will assume that the theory is Z2 symmetric, and it does not have bound states. So in principle, the last one is purely technical. You can relax it. And by Z2 symmetry, I mean I have a single particle of mass m, and it's odd under Z2. So if I have a scattering of two particles, I can only produce even number of particles, 2, 4, 6, etc. This is just to simplify life. But the first three are more serious, if you wish.
Can I ask a quick question about polynomial boundedness?
Yeah.
So some of these theorems live in the world of quantum field theory, and some of them don't. Like this.
Yeah.
What's the sort of strongest statement you can prove if
so,
you assume a UV fixed point?
Yeah. So if you so in this subject there is this, I guess, what's called a linear program, which is you start from Whiteman axioms, and then if you assume as a part of your Whiteman axiom temperedness, then you use a reduction and you get a polynomial boundedness of scattering amplitudes at physical value of momenta. Here, doing any S and T in a complex plane does not correspond to physical scattering. Physical scattering only corresponds to this, little shadows here. So here I'm assuming polynomial boundedness everywhere. Now, if you assume, for example, if you start with the S matrix and you assume unitarity right away, so I assume asymptotic completeness, people were very careful about it, so they didn't allow themselves that if you assume asymptotic completeness, then polynomial boundedness for physical momenta sort of follows from the fact that just this kernel which you integrate against the L2 wave functions have to make sense for L2 wave functions. So, so this is another way. And then there is an extension of polynomial boundedness using unitarity and using some trickery. And you can go slightly beyond the physical region, and the state of the art is this plot. So say, for physical scattering, if you take S larger than 4n squared, T has to be negative, but you can show that it's still bounded for T going to say 4n squared and being positive. So T is here for positive S is still polynomially bounded. So this is what people did, but this is the best people could do. And yeah, that's the status. I will mention now this a little bit. Now, yes, the starting point of this whole subject, first, of course, we start for, physical energy and physical angle, two real variables. And the whole subject starts from the fact that scattering amplitudes are boundary value of analytic functions. And usually it is said, okay, it follows from causality. In some sense, it is true, but it's much more subtle argument. If you go through the proofs of this results, it follows from, you start from micro-causality, things commute. So yes, it is causality. You use LSZ reduction. Then you use spectrality, which is a statement that the spectrum of your QFT is in a future time-like cone or its completion. But then it's very important and not emphasized maybe in the usual textbooks that you must use analytic completion. And by this, I mean the following fact. Imagine you have a function of one complex variable. Then if I give you a domain, let's say you can always map this, let's connect a domain to a circle, then there is always a function which you will not be able to continue through this domain. So okay, if I told you this is your domain of analyticity, you cannot do better because there are functions that are not completable. You cannot continue through the circle. And this is an example of this such functions is series. Now, if you have a function of two complex variables, the situation is different. Not every domain has this property. There are some domains which admit the completion. And therefore, if you establish based on physical principles certain domain of analyticity, most probably you can extend it. And it's only after you extend it, you can establish the properties of the amplitude. It's a curious fact about all these old theorems. And then if you use unitarity, you can extend this analyticity domain. Okay. Now, let me list the results that people did in the past, right? So first is the dispersion relation. You fix T and you have analyticity in S. This is the usual dispersion integrals. Then you fix S and you have analyticity in T. It's called the Lemon ellipse. Then there are some results about simultaneous analyticity in S and T. And then you can prove crossing and you can do extension of unitarity using unitarity. And okay, these are known domains, but I will use a larger domain. And an appealing idea which emerges from this discussion, and it's also consistent with everything we know about perturbation theory, is the one of maximal analyticity, where you assume that the amplitude is analytic in a product of C2 planes with the cuts which are required by unitarity. So I'm saying that in SNT, you just have these cuts and no other singularities on the physical sheet. So if you go under the cut, the hell breaks loose. But on the physical sheet, you have just these two cuts. And if you assume this structure for any SNT, this is called maximal analyticity. And I will assume only part of it, but will go beyond axiomatic QFT. So it will be, I will assume extended analyticity. So this is the main assumption. This is something I will
the anomalous thresholds are always on the second sheet?
No, they are on the principal sheet, but they do not appear, at least in the known examples. It's a very interesting topic, this anomalous threshold. In known examples, they appear always only if you scatter not the lightest particles. And so if you have scattering of, if you have a lightest particle and then you scatter something which is heavier, then you might run into anomalous threshold, which go beyond that. And the physics of anomalous threshold is quite interesting, but roughly you get the singularity when something happens, when you can draw a movie, this kind of Landau equation, so Coleman-Norton, where particles on shell propagate, and you can draw some process, and this is your singularities. And for anomalous threshold, these processes are such that they do not occur for lightest particles. And so here it's important that I consider scattering of lightest particles.
I see.
However, there are, apart from anomalous thresholds, there are this also issue of, I think they're called Eck nodes. Anyhow, it's an interesting topic because people try to prove Mandelstam representation, and they first thought that they prove it, but then they run into the subtleties of with Eck nodes, which are some complicated phenomena, some complicated complex singularity, and haven't been resolved. To establish that they never occur hasn't been proved, but they were not observed in the scattering of lightest particles. So this is an interesting topic for, I guess, a separate discussion because yeah, it's quite subtle. Now, unitarity, which is a statement about this unitary operator which acts in the multiple Fock space of these free particles, translate from this function t, which we care about, as a statement roughly discontinuity of t is equal to t squared, which comes out from inserting the complete set of states. And for 2 to 2, so this is a cartoon, but for 2 to 2, the precise equation is this. The discontinuity of the amplitude is equal to the integral of the amplitude, which is a statement if you insert just 2 particle state, plus the same thing if you insert multi-particle states particle production. So it equates a discontinuity to everything you can produce. It's an optical theorem. So P is a known kernel. I wrote it here. It's a sum of product of 3 Legenders, and this T sub S, it's a discontinuity in S. You go from above, from below, and this plus and minus corresponds to going from above or below the cut. So, okay, this equation looks still very complicated because in principle, if you take some random S, there is a particle production, which we don't know much about, but something magical happens, and this is a crucial use where we use it. We have a gap theory. Because if you limit your energy such that you cannot produce more than 2 particles, so if in this case you limit yourself to S between 4 and 16, this equation closes. If there is no particle production, and you have this equation in the frame where the same T enters on both sides. Discontinuity of T equal T squared. And this is something which I really enjoyed playing with because this equation does not have analog and CFTs. In conformal field theory, M is 0, and so all the cats are on top of each other. So this is something really you can enjoy only if you have a gap. And this looks quite powerful. That's a nonlinear equation on T, and we will see that it indeed very powerful. But to exhibit the properties of the sort of what is hidden in this equation, we will need some basic tools.
Sorry, before you go on,
yeah.
can I ask the analyticity, what's the difference between extended analyticity and maximal?
Yes, sorry, I haven't explained it very well. So here, imagine that you say that I'm, in my analysis, limit myself only to some subregion of S and T. I do not go all the way to infinity. So I say for my computations and for my analysis, I limit myself S to be somewhere, the absolute value of S less than, I don't know, 20, and T is less than 100. Mm-hmm. And so in this particular subregion, I assume that the picture of analyticity is the part of this picture. However, I do not assume that S and T, that this is an analytic structure all the way to infinity.
Gotcha.
So is it clear?
Yes. Yeah.
Yeah. So it's a weaker, it's extended analyticity, it's a maximal analyticity, but applied only into subregion, and so therefore you're being agnostic about the rest.
But under this extended analyticity, how do you discuss the polynomial boundedness? Because I saw you need to take T.
Yes, very, very good point. So in this way, I use extended analyticity in one variable, I go away to infinity, and another variable I keep in some subregion.
You also consider crossing. So how do you consider one is can extend to infinity, but the other cannot?
Well, yes, you can send the other to infinity, but you keep the other one fixed, right? So the point is that one of them is always less than something. And imagine what happens is that you violate the structure only when both of them go to infinity.
I see.
Because you imagine you start going, you have this picture, but now I start continuing one of the variables to plus infinity, and there is some crazy cut coming from the second sheet, which emerges on the physical sheet.
Mm-hmm.
And so there is a difference between sending only one and sending both. That's
I see.
yeah. That's,
Thank you.
so let me just explain you some basic technical tools very quickly. So one is a partial wave expansion. So if you have a function which is analytic in an ellipse, it's a very simple argument. It's known, sometimes called Neumann's theorem. So you write it as a sum of Legendre polynomials. So you can just expand in the complete basis of partial waves. And so this expansion, I'm sorry, I didn't write here on the slide what cosine theta is in terms of S and T. It was on the previous slide somewhere. Yeah, it's this 1 plus 2t over S minus 4 and squared. It's a discombination. So you can write this expansion. And based on another, if you might remember, the T of S and T obeyed real analyticity, these Fs of these Fs are known as partial waves. They also obey this property that Fj of S star is equal to F star of Js. Now this, why is it nice? It's a basis which diagonalizes, I guess, some symmetry of the problem, which is rotation invariance. What happens is that unitarity becomes very nice in this basis. So in particular, if you try to consider the states with a given angular momentum, which is J, the unitarity becomes a statement that this combination Sj of S, which is 1 plus f of j, and you should think of this 1 as coming from the disconnected piece. Remember, the full S matrix was disconnected piece plus connected, so 1 is disconnected piece, and fj is this thing, and then the unitarity just tells you that this absolute value of this thing is less or equals than 1. And the elastic unitarity tells you that Sj of S is 1, which in terms of f is this equation, that imaginary part is equal to f squared. So you might think, okay, so what's exciting about that? Sj of S is equal to 1, so S of J is just pure phase in this region, but you will see now. And to see what's nice about this is that let me introduce something known as a Froissart-Gribov formula, which is lately is called in the context of conformal bootstrap as inversion formula. And this is something where extended analyticity is being used. You start with f of j. It's defined as a projection of your amplitude on a given Legendre polynomial. So this is the definition. That's the first line. And you can rewrite it as a certain contour integral. So you rewrite it as a complex contour integral, where this qj is a solution of the same, Legendre polynomial satisfy, or Gegenbauer polynomial satisfy differential equation. Qj satisfies the same equation, but its discontinuity is given pj. So if you close this contour on the cut, you reproduce the first line. This is just some simple mathematical fact. And now what you do is that you deform the contour. You drop the arcs at infinity using polynomial boundedness. So you assume this, and you wrap the contour around the cuts. And what you get is that fj of s is now given by some integral over discontinuity in the T channel. So this is sub T means discontinuity in T against this Q Legendre polynomials. And what is nice about this formula and what is being used all the time in CFT bootstrap is this formula is you can analytically continue in spin. In other words, you start with this function define an integer j, and then this formula is manifestly a Bayes-Carlson theorem. So there is a canonical analytic completion. In principle, if you consider non-identical particles, there are two analytic continuation. Here I'm considering identical particles, so there is just one function, which is analytic and spin. So this is something nice that happened, which is that now we have this f of j is defined for any complex j in principle. As soon as we can drop this arcs, which becomes a statement that the real part of j is larger than this Regge exponent. Now you see something, you might play some interesting game, is that if you look at elastic unitarity, and this equation was defined for integer j, but now If you think about this, you find that what we just did, both sides admit a unique canonical analytic completion, not unique, but canonical, which allows you to analytically continue also, which allows you also analytically continue this equation to any complex J. So we start with some elastic unitarity being some statement about S matrix being pure phase for real J, but now you get some equality for any J. These Fs now defined through this Froissart-Gribov integral. And the right-hand side I was just explaining you, we just derived it. And the left-hand side, you take imaginary part, and it's defined by taking you take a discontinuity Fjs plus I epsilon, Js minus I epsilon, and then it gives you a second discontinuity in S. And this second discontinuity of the T of T is known as a double spectral density. It's a double discontinuity of the amplitude. It's defined here. So you have two cuts, and you go above, above, plus below, below, and you go minus above, below, minus above, below. That's the discontinuity. And the nice thing about this object that it's crossing symmetric. That's something that happens. Now we analytically continue this elastic unitarity, and now before we started elastic unitarity being the statement for S being between 4 and 16 and T being negative and in a certain strip, but now we seem to be we continue that in some larger domain. So what is this domain? And another way to think about it is due to Mandelstam, and he did it in 1958, long time ago, where he started with elastic unitarity in the form I explained to you. So it's a discontinuity of amplitude is equal to amplitude square. And he continued in T. So starting from physical T, which was negative, he continued it to arbitrary T. And the trick to do it is very similar to Froissart-Gribov. You write your amplitude as some Cauchy integral. You write your discontinuity as these Cauchy integrals where you use analytic properties of the amplitude. And then you deform the contour. Very similar things happen. You wrap around the cut of the amplitude, which is something you know from this extended analyticity. And you get the following equation. And this is what I call the Mandelstam equation. So Mandelstam equation is an analytic continuation of elastic unitarity in T. So you see this, there is this any T here. And the structure is a double discontinuity of the amplitude is equal to the square of a discontinuity of amplitude in the dual channel. So we look at S between 4 and 16, but we look at the square of discontinuity in the T channel. And the precise formula is this. So that's, there are some maybe symbols which you might be confused about, but hopefully slowly we will clarify some things. And the kernel is explicitly known, and this is what it is. So something interesting that follows from this analysis from analytic continuation of elastic unitarity is this picture. So on this plot, you see S and T, and what I draw here is the structure of a double spectral density rho. So first of all, there is this region in gray where double spectral density is 0. This is, I called it here Steinman shadow. This, because it's closely related to this Steinman relations. I don't know if you might have heard that people also used recently that the discontinuity and the overlapping channels has to be 0. It was historically derived by Steinman, and overlapping channels in the simplest case here, you see they cross S and T. This is a 2-to-2 amplitude. And if S and T are physical, you can show based on essentially unitarity. Again, Steinman relation is just a consequence of unitarity, that the double discontinuity for the physical kinematics is 0. And usually people use it for high point amplitudes because in this case, you can really reach kinematically this overlapping discontinuities without analytically continue unitarity. Here, if you want to go to overlapping channels, so you want to go S and T higher than 4 and square, you have to continue unitarity like Mandelstam did. And if you continue unitarity, you see that there is a region. So the normal threshold in S is 4m squared, and normal threshold T is 4m squared. You might have thought that if you go above both thresholds, the double discontinuity is non-zero. But actually, unitarity tells you that there is a finite region where it has to be 0. And this is a consequence of unitarity. So this is a very close cousin of Steinman relation, I guess. Simon was emphasizing this maybe. And then you have some structure where if you stay in one of the variables between 4 and 16, so it means you have in this elastic region, you just produce one particles, and so you can, in this region elastic, you can use a Mandelstam equation. So your double spectral density here is defined through this equation. You see S between 4 and 16, and rho is defined as double disk. The same here. So here, if you wish, we have control over double spectral density. When both S and T are larger than 16, this is this hard multi-particle region. This is where the dragons live, and this is where all the complicated stuff live. Complicated physics, which would be interesting to discuss in some other occasion, maybe. Now, the lines of support along which the double spectral density is developed are called Landau curves. This is just a jungle, and they have known shape. And you derive them following the steps that I did. So these equations, they just follow from kinematics. And any relativistic amplitude 2 to 2 QCD, it will have this structure. So this is a completely general thing. Now you might ask, what is the relation between this Mandelstam equation and what I told you about analytic continuation of partial waves in spin? The relation is that if you take the Mandelstam equation and integrate it both sides with this Qj, then this kernel has some magic properties, and it becomes a product. And anyhow, you just recover this equation analytically continued in spin. So if you wish, the structure which I told you is that if you have extended analyticity, you have analyticity in spin, and you have elastic unitarity continued in spin. You can also derive Mandelstam equations, and the two are related by this integral transform above. So in this way, you might think that, okay, the physical meaning of this elastic unitarity continued in spin, another way to think about it is in terms of this Mandelstam equation. And what is really nice about it is that what enters is this rho, which are base crossing symmetry, and this was manifested in this picture. If you reflect it along the diagonal, it should look the same. So any questions at this point?
Can you maybe very quickly about these Steinman conditions?
Yeah.
So if I take I assume if I take just some Feynman integral, I would expect that I can do the same things that you're describing.
Yes, absolutely, yes.
So say I take some box integral.
Yes.
Which has a log s over t squared. So what would be the statement about that integral?
So I think you're probably thinking about massless.
So it's okay. So here it's very important that you have a gap. Otherwise, this region just.
Yes. You see that this strip is 4m squared and 16m squared. If you set m to 0, it all collapses.
Okay, makes sense.
So this is very important.
So maybe you can.
Sorry.
Oh, well, okay. Maybe I'll ask first. This analytic continuation in terms of J. Maybe I missed it, but can you go back in terms of the original partial waves? How should I think about that?
Yeah, so the original partial wave, if you define it in terms of the integral with Legendre, there's no way to think about this in this way. But you can do this contour deformation, and now you're integrating against this Qj. And because of this Cauchy theorem, when J is integer, it is the same as doing the integral with Pj. But now this Qj is very simple analytic properties in J, and you can consider this Qj for J being complex. And then Fj is just defined as the integral of discontinuity of the amplitude against this function. So this is yeah. Any other question?
Can I ask a follow-up on that?
Yeah.
So one thing we're used to is for example, the 2D scattering in the classical region. In that case, the J is like literally total angular momentum. So it's not so strange if it's not an integer. I don't know how to think about that if J becomes complex.
Right.
What's the meaning for J being, for example, imaginary or complex values?
Well, I guess yes. So one way you can think about this is, first of all, this J, if you take J to be large, it essentially becomes impact parameter. So this is a relation. Now, if you take J to be complex, maybe the one physical example, if you have a theory and you look at the high energy scattering, it will be dominated by, for example, by some Regge singularity. And if your amplitude at high energies is not purely real or purely imaginary, you will have that this Regge singularity is in a complex plane. And then if you wish this complex J is maybe control sum. This complex J is some effective description of physics, which includes both production and scattering. So that's one example where complex J show up. It's in the Regge theory. Otherwise, it's a formal. And actually, maybe I will not use a complex J, so I will just use a real J, which. So maybe can.
Thanks.
Yeah. Okay, so let me now try to explain a bootstrap scheme in the last, I guess, 15 minutes or a bit less. So now, first of all, bootstrap needs positivity. If you just have something crossing symmetric, it's not enough. Usually, you want have some positivity. Now, based on what I told you, you can figure out that for, say, positive S and T, this function rho is real. It's crossing symmetric, and moreover, there is this simple result. Again, it's an old result that close to the leading Landau curve, there is a region where it is strictly positive if you have non-zero scattering. And the argument, roughly, let me just tell you that quickly, is that you have this equation, and on the right-hand side, you have a discontinuity. And if you stay in this region, this discontinuity, you apply to it an optical theorem, and if there is a scattering, it will be positive, you can argue, and then the whole thing must be positive, because this kernel here, it happens to be also positive. So then you see that if you have a scattering, then everything on the right-hand side is strictly positive, and then you have a region where it is positive. So this is some fact, and so therefore we have something crossing symmetric and strictly positive definite, so we can play some interesting games. So here is what Thomas was asking. This is known as the Axe theorem, which says that if you have a scattering, then you must have production in D larger than 3. It again assumes extended analyticity, and the argument is as follows. I told you that from elastic unitarity, it follows that there is this Steinman shadow region where there is no rho. But here I restricted myself between 4 and 16 because that's where elastic unitarity was valid, right? Now, if you assume there is no particle production, it means that elastic unitarity is valid at arbitrary energies. Then what you get is that this region where it is 0 should be extended, and in particular, you will get that everywhere below the red curve, the double spectral density have to be 0. By crossing everywhere below this blue curve, it has to be 0. However, as I just told you, the fact that you have a scattering in the Mandelstam equation implies that it has to be strictly positive. So therefore, you have a tension between crossing, the fact that there is a scattering, and the fact that there is no production. So scattering tells you that rho has to be positive here, and on the other hand, in a crossing channel, you get that it has to be 0. Therefore, you have a contradiction, and there has to be a particle production. So maybe one way to think about it, if you forget about blue curve and just think about the red curve. So from elastic unitarity, you will conclude that everything below the red curve, rho has to be 0, and rho here has to be positive by the fact that there is a scattering. And now you try to draw a crossing symmetric picture. And what you'll find that where you were concluding that rho is 0, rho has to be positive suddenly, so you get a contradiction. So this is known as the Axe theorem, and it's crucial to use D larger or equals than 3 here. Because in 2 dimensions, you do not have T, you do not have rho, and all the structure is lost. And but now you see that in these higher dimensions, on one hand, the higher point amplitudes get more complicated, but you see that elastic unitarity already tells you, controls the productions, and therefore, if you manage to implement in your bootstrap scheme elastic unitarity, you will have some production, and that's a basic idea. Any questions about that? So let me now try to explain the bootstrap scheme. It involves few steps. I don't know if I will be able to explain, but I'm sure that we'll be able to explain the main ideas. So So the starting point is something we can call the threshold expansion. And the idea is very simple. We have a non-perturbative problem. There is no small parameter. If you want to do the concrete computations, we need a small parameter. I don't know another way to proceed. So there is a natural candidate, and and this is a volume of the available phase space. In other words, if you have this elastic unitarity relation, discontinuity of amplitude is equal to amplitude square, here there is a phase space available for the particles. And when you send energy to 4n squared to the threshold, it shrinks to 0. So sigma s is a parameter which becomes small if you send s close to 4. And essentially, threshold expansion is an expanding at low energies, which is a sigma s. So in particular, let's solve elastic unitarity close to this threshold. So this is the most general solution of elastic unitarity for partial waves. This part with logs and s minus 4 is universal, and all the dynamic in data is in this bj, and this bj is a meromorphic function that follows from elastic unitarity, and the leading scaling was sigma s, which is sigma s to the j. It follows from Froissart-Gribov. Actually, this 1 over aj are called scattering lengths. This is what's usually measured on a lattice in a scattering experiment. Now, one comment which I wanted to make, maybe not maybe not so widely known, is that in even dimensions, the nature of a singularity is just a branch cut. It's a square root, d minus 3. But in odd number of dimensions, it's a 1 over log. F has 1 over log. In particular, if you go under the cut, the Riemann surface has infinitely many sheets. And in even dimensions, it has only 2. So this is some interesting peculiarity. But anyhow, so at this slide, we solved for elastic unitarity close to the threshold. All the dynamical input is in these coefficients, Bij, Aj, and here also for scattering length of spin 0, it's a little bit subtle, but essentially, again, you have few parameters. So now any theory will have this form close to the normal threshold. Now this is my input. On this slide, I was telling you there is a low energy, low spin data. This is the input. We solved the elastic unitarity. Now, the next step, you note that this solution of elastic unitarity translates to the threshold expansion of the discontinuity of the amplitude. The way you work it out, you take the expansion in terms of Legenders. You take the discontinuity, which is the same as taking the imaginary part of this f's. If you use the formulas from previous slide and you go to close to threshold, s close to 4, you find that the imaginary part of f scales like s to the minus 4 to the 2j, and Legendre polynomial scales like s to the minus 4 minus j. So all the higher partial waves are suppressed. Therefore, you find that this data for partial waves, for low spin partial waves, turns into the threshold expansion of the discontinuity of the amplitude. And note an interesting thing that this argument does not work for the amplitude itself, because if you try to repeat it, you will find that this sum blows up, and this is really something for the discontinuity. But because we will use the Froissart-Gribov formula, which is formulated in terms of discontinuity, we will be lucky, and this will be enough. Now, next nice thing happens is that if you look at the Mandelstam equation, which remember formulates the double spectral density in terms of the discontinuity square, there is some region of integration here, which follows from, again, the kinematics. And what happens is that when you sit close to the Landau curve, which is a region where rho becomes non-zero, this region shrinks to 0. Therefore, if you go slightly above Landau curve, this region is in both variables, this eta 1 and eta 2, are close to the threshold. And so the threshold expansion for this continuity close to the normal threshold maps to the threshold expansion for the double discontinuity close to the Landau curve. So this is what happens. So the punchline here was this. I tried to explain you the first scheme. Let me recap. We start with Fj. We solved elastic unitarity for that. Is in terms of some parameters. We used partial wave. We got the threshold expansion for the first discontinuity. We use Mandelstam equation and elastic unitarity to find the expansion of a double discontinuity of the amplitude close to the Karplus curve. And then we can use crossing to map it to this other region. So, because the picture is symmetric, you can use crossing to make a prediction in the cross channel also about the behavior of a double discontinuity. Now this is a structure close to threshold. Now you map it to, you can use Froissart-Gribov formula and crossing again to map it to the large spin expansion of the partial waves. This is very symmetric, similar to CFT bootstrap. What happens is that if you plug threshold expansion in a Froissart-Gribov formula, it generates 1 over J expansion. I will not say much about it. I'll just say that if you take this integral and you try to crank out J, what you find that this integral is dominated by small z close to the threshold, and therefore there is a direct mapping. The expansion in this sigma variable becomes expansion in 1 over J. So now you can find both f and imaginary part of f by knowing the behavior of discontinuity and double discontinuity close to its threshold. And moreover, so if you want to do this threshold expansion, you can do these integrals exactly. There is this neat formula that we derived, that if you take this z minus z1 is the same as sigma s. And so you can integrate in the Froissart-Gribov formula against Qj exactly. You get Qj in some other dimension with some other spin, but it's an exact formula. So we don't really have even to expand in 1 over J, but physically, this is what dominates the threshold physics. Now, let's look at this picture again. I think it's the most important picture in my talk is that, and let's think of scattering in the S channel. So S is above 4. So first we start from elastic unitarity here, and we solved rho close to this red curve. Do you see my pointer?
Yes.
Yeah, so we solved, we start with by discontinuity solving close to normal threshold, and now we solved for rho close to this red curve in this region 4 to 16. However, by crossing, we know that the same expansion is valid here along the blue curve, just because it's the same crossing symmetric function. However, in this region, S is larger than 16. It's actually larger than 64 over 3. Therefore, it's a region where it's already analyticity kicks in. However, we will see that the analyticity is controlled by this low energy, low spin physics miraculously. And the way it works is, let me consider this ratio. Let me call it R of G. And this ratio is built such that just if you have elastic unitarity, this ratio is 1. So the R is 0. This is elastic unitarity. Now, using this threshold expansion, you can find this R in some region in the inelasticity region, and you find that it has a universal form. It's linear in J, so it becomes if you wish, scattering becomes very inelastic there, and its leading form is completely universal. So this ratio of lambdas, it's a known function. It's plotted here. In particular, it takes maximum at s equal to 40m squared, and it's roughly equal 1.6. So that's just follows from the consistency, and and there are some corrections. So just to emphasize that there is a universal prediction for inelasticity based on this picture at large spin. Now you can say, okay, large spin is good, but what happens at finite spin? And since my time is up, I will be very brief. So here it's a crucial point, which is, if you wish, it's an interesting thing. It's a general point both about all kinds of available bootstrap, CFT bootstrap, scattering amplitude bootstrap. If you want to put error bars on the formulas that I write, you need some local bound on the discontinuity. And for the discontinuity, we expect we have some behavior close to threshold. At large T, we have some T, some Reggie behavior. And at intermediate energies, we can have some bumps. We can also call them outliers. So if you know from the experiment or from somewhere else the side of these bumps, or you can consider it as a parameter of your game, then if you bound this threshold expansion and with some parameter, you then just use this parameter, run it through the whole game, and you get the predictions for the partial waves at given spin and given energy with the error bars. So if you wish, it's maybe not here, so it's not so surprising. I start with the threshold. I computed everything in terms of the threshold, and then now I put a bound on the error bar. I can, of course, compute the errors, but there is no known rigorous local bound on the discontinuity, and so if you want to use formulas for finite J and finite S, you need this extra phenomenological input if you wish. And let me wrap up about numerics. So basically what you do in the numerics, you expand the amplitude in some basis. So in terms of these raw functions and this alpha variables, can I have maybe 3 more minutes?
Sure, no worries.
Okay, thank you. So let me explain a bit. So what these guys are doing, which I guess inspired us to think about it. So you start with the amplitude, you expand it in some basis, which is by construction a base is maximal analyticity. So this is the picture. And the information in this parameter is alpha, and you truncate the sum. And these alphas are choosing such that crossing is automatically obeyed. So then you satisfy crossing, you satisfy elastic, you satisfy maximal analyticity. In their case, you want to impose unitarity. Sorry. And one important point, maybe, which I want to emphasize is that this numerical ansatz for finite and max never can satisfy elastic unitarity. The way you see it is you just take a double discontinuity and you see this numerical ansatz has non-zero raw everywhere. It cannot have this region of zero double spectral density. So this is a basic problem with this ansatz, I would say. Of course, you can hope that when you don't truncate the sum, if you go to infinity, then something will develop like this, if you are lucky. But there is no good reason for that. And so one obvious way to try to improve it is to impose the structure where you want to have this region where rho is zero, or in other words, to impose elastic unitarity, which is not being imposed in the current bootstrap. Why elastic unitarity is not being imposed is the following. So you start with these partial waves, you want to impose unitarity, which is something is less or equal than 1. And the trick is to rewrite it as a semi-definiteness condition, and then you use some solvers. And the point is that elastic unitarity is a statement that something is actually equal to 1, and it becomes a nonlinear equation, which is not clear how to implement numerically, but it's also clear that it doesn't make sense to implement it numerically in this way, because then your ansatz clearly violates it. So we should do something else. And so the basic proposal based on our understanding is that we can try a few things. Is that, well, one can try to impose a consistency with a threshold expansion. One can try to impose elastic type unitarity type, which is this condition less or equal than 1 at non-integer spin. Physical theories satisfy S of j equal to 1 at non-integer spin. But clearly, if you impose something like this at non-integer spin, physical theories are still part of that. This goes beyond what can be done. And you can also impose a slower bound on inelasticity if you make assumption, if you make some parameter on what you assume about discontinuity, then you can also implement a slower bound on inelasticity into the numerical bootstrap scheme. And the crucial point is that all these conditions are linear in these parameters alpha, and so they can be implemented with semi-definite programming. So that's it's a basic idea. So let me conclude. I have a comment on CFT if you ask me how does it map to CFTs, but let me just conclude. So there is this interesting interplay between extended inelasticity, elastic unitarity, and crossing. I don't know if there is any chance to prove any of these things. I guess people have tried for many years. Maybe then they stop, but anyhow, that's an open question. Then I briefly mentioned that there is this interesting challenge of implementing the structure of rho, which I showed you numerically. And because we use this threshold expansion, we can use low energy, low spin experimental latest data, and maybe we can make use of it. Finally, there was this region, which is a multi-particle region, and it's very complicated, but I think there are some parts of it which we can still make some progress. And well, we all, I guess, we all this in principle, all this analytic structure is completely universal, but it would be really interesting if we can solve some concrete theory, and this is an open problem. So it would be interesting to try, and maybe we haven't tried the right theory yet. So yeah, thank you then.
Let's thank Sasha. I'm going to unmute everybody, and then we can properly clap. Now let me mute everybody, and then unmute yourself to speak.
Yeah, maybe I can ask.
Wait, sorry. Unmute.
Okay. So here you proved many things kind of non-perturbatively and from first principles. But some of these things, for instance, this equation that you showed when you solve elastic unitarity. So in the threshold expansion, these things have been shown also to follow from like very basic principles of effective field theory. For instance, where people look at, I think it was a bit later. Sorry, earlier. Yeah, so these equations below, I think, is that equivalent to this, what people call this effective range expansion, when people think about like nucleon scattering or something like that, which is also basically purely elastic. And could I think of some of the things that you're doing as trying to, like when you expand your scattering amplitude as some polynomial and then you try to constrain it, could I think of it as trying to put some bounds or constraining some weight Wilson coefficients of some EFT? Or
so yeah, I guess so. The first part, I think that's what people essentially this is what people do, maybe in a slightly different language, but this is low energy expansion. And if you have some effective field theory, surely it will obey that. If you do the computation and with some coefficients, this will encode some coefficients within low energy theory. That's for sure. Now, here, and what I did, I was not putting bounds on these coefficients. So I was using this. I was saying that if you use this coefficient as an input, then let me try to constrain this the whole structure of the amplitude in terms of this coefficient. However, you probably can reverse the logic and try to play the bootstrap game where you try to maximize some of these coefficients. Probably. So in what I was doing, I was not doing that, but I think that should be part of the game, at least for this particular guys, 1/8 of the J scattering lengths. This is what people already did without implementing elastic unitarity. So then you get bounds, upper and lower bounds on scattering length. People actually did it in the 70s also. So here, maybe the idea would be that now if you try to impose elastic unitarity, these bounds should get tighter. Maybe not, I don't know. But this is some game you can play. And this is what we are now exploring numerically together with Madalena.
thanks.
Are there more questions?
Yeah, so I saw you in the very end of your conclusion, you have a comment on solvable model. Could you say more on that?
Oh, well, I wish I could, but this is you mean this?
Yeah.
Yeah. So, well, what I mean by this is the following. So if the game we are playing is that we say we do some analytical analysis as far as we can, and then we rely on the computer, and then you try to get the bootstrap plots, and maybe if you find there a cusp or some special feature, then if you like is this cusp, and this was my very first slide with the 3D icing, it corresponds to some physical theory. Sure. And then by zooming on this cusp, you can try to solve it. My point here is that, as far as I know, based on the old literature as well as new literature, this sort of game has not been exhaustively played, and therefore there is still some hope. And I don't see a fundamental reason why we can solve high-dimensional CFTs and why can we solve two-dimensional S matrices. Why can't we solve a special S matrix in high D in this way, or partially solve? Why not? And as far as I can see, this hasn't been explored, this possibility.
Thanks.
So can I ask one question?
Yeah, go ahead.
So can you, with this numerical method that you were proposing, so can you get the pion scattering in 4D
Well,
from these analyticity constraints? And then can you compare that? So people are starting to measure 2⁻³ scattering of chiral Lagrangians on the lattice. And then can you compare like their lattice results to what you're getting from your nonperturbative formula using only physical, like using these, well, physical constraints where you don't know a priori if all your assumptions are really realized or not?
yeah, strictly speaking, you don't, and so if you wish, it will be a test of this assumption. So first is there was a paper which I mentioned at some point last year maybe, where people use this numerical bootstrap without elastic unitarity to constrain pions. So I suggest you look there. It's Pedro Vieira, João Penedones, and Andrea Guerreira. I think it's where they impose different parts of. They assume slightly different things, and what they got is that they got results which are consistent with the experiment. So they got some regions. Well, I don't have the plot, but roughly you get some islands of allowed scattering length, and you just find that they're consistent with the experiment. Now, I guess what we are proposing, unfortunately, I don't have a concrete results for pions yet, but in principle, everything I said you can do for pions. The hope would be that you get a better bounce, and if you are incredibly lucky, because there is a sort of a big philosophical open question, is that what I was proposing here is that we are being maximally agnostic about this multi-particle region. Maybe we can go a little bit there inside, but I didn't tell you much. And so the question is, can you actually solve a theory without talking about this region? In other words, let's say you play some variation of this game where you find a numerical algorithm, maybe what I was telling, maybe you can find a much better one, something completely else. Yeah, let me emphasize that no one ever came up with a good algorithm which implements the structure that I told you about and implements unitarity, and you can run on the computer. This is an open problem. So what we are trying to play here is some games, but if someone comes with a better idea, this would be great. So now, in principle, what I told you, we can try to repeat or extend this analysis of these guys that I mentioned, and we will get some better plots. And so in some dream world, you will find that there is some exclusion principle. And I'm sure we will find something which is consistent with the experiment, or we can check with the lattice. But the really exciting thing would be that if you find these things on the boundary. But I think the short answer, yes, we can do it for pions, and we can compare. Yeah, I am aware of this recent 2 to 3 results. I think people at CERN work on it actively. So hopefully, yeah, will be something more concrete to report. So yeah.
Can you say something quickly about CFTs that you were hinting at?
Yes, something about CFTs. So because for those of you who care about gravity, you might be really disappointed by the fact that gap was so important. So let me maybe say something interesting for you. So there is a very direct map from what I told you. So this is a table, you can see it. So this is S matrix element, CFT. Amplitude, it's a correlator. discontinuity of the amplitude is a double discontinuity. The double discontinuity of the amplitude, which is rho, is a quadruple discontinuity. Fj's are Cj's. Froissart-Gribov formula is known as Lorentzian inversion formula, which was found by Simon. And dispersion relation also was recently derived, CFT dispersion relation by Dean Carmi and also Simon. So, okay, CFT is of course is gapless, but on the other hand, if you think of it as living on a sphere or a gravitational theory in a box, then it is gapped, and there is a sort of cousin. Yeah, and let me mention that. So here we studied the consistency conditions that follow from crossing and positivity of rho on the left-hand side. This quadruple discontinuity on the right-hand side, it was not studied. Really, it was studied in a very few papers, very briefly, and it's a very interesting quantity which somehow goes beyond the. It's also complicated to study, but it's an interesting, not very well studied quantity, and might be something interesting from studying its crossing. Then you can ask, okay, so the whole thing with elastic unitarity was based on the fact you have a gap and you have two particle states and nothing else. There is something similar in CFT. I worked on it also recently, and still, which is known as a Polyakov conditions. And a Polyakov condition is exactly the same type of thing. It's a consistency conditions of two particle states, but an ADS. And it seems like if you start imposing Polyakov conditions, you might be getting some interesting. This goes a little bit beyond the current conformal bootstrap. And so there is this connection or suggestion, but I don't know how precise is this analogy, but it seems to have some sense in it, because both things is a consistency of two particle states. And if you wish, then if you want to translate my talk to CFT language, the question would be, can you study Polyakov conditions together with the crossing symmetry of quadruple discontinuity and get something interesting? And this hasn't been done. So this would be a CFT question.
Okay. Are there any more comments or questions?
Yeah, maybe just quickly, because I'm still confused. So in the CFT bootstrap, usually you try to put bounds on the spectrum or the OP coefficients, right? So here you fix the spectrum. Is that right?
You mean I fix the spectrum of, well, there is a parameter M in a CFT. You say, if I have an operator with dimension delta, I bound, the next heavy guy, right? But you start with assuming that you have an operator of dimension delta. Here, I'm assuming I have a particle with mass M.
So in a sense, you would be constraining the spectrum beyond the lightest state.
Yes. So in CFT, the spectrum is trivialized, right? Because you have a one particle state, and then you have a two particle states and three particle states. So this is what happens if you wish to this. This is the analog of CFT spectrum. It becomes continuous and sort of trivial, but what stays is the OP coefficient. So here, I assume that there are no bound states. There is also a game you can play where what is there's a bound state. So this would be a little bit more analogous. Here, in a sense, yes, the spectrum is fixed, at least in the setup I was telling, and so I was playing with a bound of the value of the correlator on the OP coefficients. This is more.
But in principle, you could add a bunch of poles below the cut.
You can add, you can add bunch
and then
of
play
poles.
the game of constraining double trays in terms of single trays. The output of that for
yeah. Exactly. This would be if you add an extra pole, which will be like adding a single trace, then everything I said will slightly change because the leading singularity will be this pole. So you will get the constraints on the double traces, which is like two particle states in terms of single traces. Yeah.
Okay. Well, we should thank Sasha again. So thank you.
Thank you.
Do a virtual clap.
Thank you.
Let me stop recording.